we're slowly progressing towards giving you the ability to modify AI towards your personal needs. But before we dive into that subject, let's talk about how AI works and dive deeper into the mechanics of AI so we can better understand what we are modifying and to what ends. Again, you can upgrade your knowledge about AI way beyond what we'll show you here today by joining our Tech Bootcamp, the invite link to which is in the description below.
It is worth today diving a little bit deeper into what we would call the stack. And you probably have heard this word around somewhere before, but a stack is the layers of technology that make a service possible and how all these layers interact to produce what we ultimately use. So blockchain has stacks, VR has stacks, a website has a stack. A stack is just a word that we mean to describe what extends from what you're seeing on the screen down to the actual hardware. And there's a lot of different levels of resolution or levels of fidelity that you could bring to a stack. For AI, we've simplified it to this structure. At the top, we have the UI. That's what we're looking at now. UI, or user interface, is what you're looking at on the screen. Below the UI, you have the AI model. The AI model is what you're interacting with, what you're sending things to and getting things back from. An AI model is just a bunch of math. You can literally, if you had enough printer paper, you could literally print it out. It's not doing any thinking. It's just a bunch of statistical weights, a bunch of probabilities. Below that is the data, and we've put data and the internet together. You could separate these out if you wanted to. The data is what the AI model was trained on, and the internet is how it communicates between your computer and wherever the AI model is. And the AI, wherever the AI model is almost certainly on something called a GPU. A GPU is a special kind of chip that does the kinds of calculations that we use in AI very well. And they're a necessity for most of the things that we're doing. Your personal computer has a GPU, but it's probably a very small one. And so likely if you're using an advanced AI model, you're using a GPU that's somewhere else. And we'll dive a little bit more into what that means and importantly, how you do that. So starting from the bottom and working up our way up, let's start with the GPU. There's a lot about GPUs in the news today because of the announcement of the US export controls on semiconductors to China and the limitation on sharing those that intellectual property with Chinese companies and government. GPUs come in a lot of different shapes and sizes, but they're a huge competitive advantage to AI. Most of the math that we use in AI, most of the models, the fundamental concept was really hashed out in the 60s and 70s. Let that sink in. Most of the mathematical breakthroughs that contribute to the AI we're seeing today were created in the 1960s and 1970s. So why the heck did it take us this long to get here? The reason is this thing called GPUs. Even though conceptually a lot of the breakthroughs had been made decades ago, there wasn't sufficient computing power to make them real. This didn't stop people from trying. People invested a lot of money into AI and it failed spectacularly, which led to a massive period where there was no investment in AI that lasted so long that it's referred to as the AI winter. However, what happened during the AI winter is something very interesting, which is video games did get a lot better and better. And part of why video games got a lot better was because of their graphics. And to make better and better graphics, you needed these better and better GPUs. GPUs are like a really, really fast CPU. They're still a normal type of computer. They're still doing math in many ways, they are still similar to the computer that you have in front of you. Now, it just so happens that the kind of math, the kind of computations that you need to make these really high quality video game graphics is pretty much the same as what you need to do AI. So there was all these kind of like weird researchers in universities who were focusing on AI and were never going to make any money off of it. And then all of a sudden they were like, oh, wait, hey, we could use these video game chips to run our AI. And that's why we see this explosion of activity today. That's why it seems like all of a sudden we're advancing leaps and bounds every week, is because the methods we're capitalizing on methods that have existed for decades. We're capitalizing on decades worth of methods that now have the computing power to become a reality. Now there's a global GPU shortage because so many people want to use them for AI. And so they're getting more expensive. You see the United States government forming things like the CHIPS Act explicitly to make sure that we have enough GPUs to fuel this. There's billions of dollars going into this. Part of the reason why there's this shortage is the very complex and ongoing supply chain disruptions happening in the post-COVID world, in the current geopolitical environment. Another bottleneck is the types of equipment that are required to make GPUs are very difficult to make and are isolate the capabilities for certain kinds of GPUs that are both of a certain size and of a certain speed is isolated to just a few countries, including the United States and one or two countries in Northern Europe, if I understand correctly. And so that's part of why limiting use of that equipment to China actually is very impactful to their industry, because it's not easy to construct those machines, and the methods for doing so aren't well known. A lot of stuff goes into this silicon. There's a lot of like metals. There's a lot of stuff that comes out of that goes into this technology that has ethical issues with how the materials are sourced, but we can make more of them, and we are, which is part of why the US government is putting so much money with the CHIPS Act into that. Most people access GPUs in the cloud. What does that mean? It means that you create the inputs on your screen, but then all the computation happens somewhere else in a data center somewhere and then comes back to you. This is because GPUs are very expensive. And so usually you don't want to own a bunch of your own GPUs. You want to borrow someone else's GPUs. And so you rent them by the second or the millisecond from someone like AWS or Google Cloud or someone similar. So then we have this layer of data, which we're associating data with the internet. Usually you would associate the internet with networking, which it is, which is how the computers communicate with each other. But in the case of AI, it's also part of the data. All of these AI models we're using, these really big ones that can do a ton of different things, that can perform all these different tasks and make any kind of image or make any kind of text if you know how to talk to them, are trained on massive, massive data sets, literally terabytes of data. And there's only one place to get this much data in an organized format, and that's the internet. Anytime you're on the internet contributing data, you're organizing information for free. And so all of these models take all of that human activity and compress it down. And so, examples of this are on Pinterest. Every time you post something on Pinterest, you're creating a pair of a piece of text with an image. And so then when you're training a text to image model, you might use the Pinterest data set along with others. For GitHub, you're creating these big structured collections of code. So then when you're training a code generation model, you're contributing to that by posting on GitHub. If you want a model that answers questions, then you're doing that on Reddit, where someone posts something and then the answer is posted. And you could filter from these kind of shorthands on Reddit. There's things like explain like I'm 5, or today I learned. And so these then become ways for the computer to automatically detect different kinds of human interactions and reproduce them. So yesterday we were talking about the kind of ethical implications here, that you're taking all this work that other people did and you're putting it into the model and then you're reproducing it. And it's not very clear how any of that credit gets back to the original creators, if any, and the legality around this is still very blurry. We mentioned yesterday that the laws around this currently are very laissez-faire. The precedents that are being formed are that you can't be sued for having copyrighted information in your underlying data set, at least in the United Kingdom. And so the gravity is toward letting people create these models with web scrape data sets. Any new model can be thought of as a compression of human activity on the internet. So if you wanted to make something that wasn't just text or image or code, the way to think about it would be, what's something that people do on the internet all the time, and what would a model look like? So some people are looking at decision transformers. Something that people do on the internet all the time is click things, right? And make decisions about where to go. And so there's people working on AI models to replicate that. And then when we'll look at this a little bit when we get to the practical, people are then taking the data of how people are interacting with the AI models and then feeding that back into the model. So this doesn't happen live. These models don't learn live and continuously when you're interacting with them, but you can then take what people are doing with them and then use them to change the model or improve them. You'll hear this word a lot if you're reading about generative AI. It's this word transformer. This is a architecture that goes into basically any big AI model these days. And there's certain kinds of transformers that are used. They're different for image and text, and there's other things that are attached to the transformer. But this is kind of the underlying format that is converged on. A few years ago, there was lots of different kinds, and then this one has just kind of become the one that works. One of the reasons why it works is that you can feed in unsupervised data, and the data doesn't have to be very high quality as long as there's a lot of it. So that's another reason why we're seeing this big breakthrough, is that people figured out that if you put in a lot of low quality data, you get the same results, you actually get better results than if you put in a smaller amount of very high quality data. What do I mean by high quality versus low quality? A high quality data set for text would be one that's very carefully selected to have only high quality text and make sure that there's no pages that have any weird artifacts or HTML tags or things that would muddy up the data set. Instead, they've realized that a lot of low quality data works just as well. And this was first kind of like, not first outlined, but a popular paper about this is called The Unreasonable Effectiveness of Data. This was by Peter Norvig, the head of Google Research. And he basically said this, that for the next 10, 20 years, as long as we dump enough in there, it will get better. And we have not found the limit of this yet. GPT-3 currently is the largest, and Bloom are the largest of their kind. They were much, much high quality than GPT-2, which was the biggest one before that. There's non-open source models like Palm or WuDao or any number that we are allegedly much larger than these models, and they're still getting better just by putting more low quality data in there. So you need a lot of this to make these models. And once you have the data, you need a lot of computing power. There's estimates that for Palm, the amount you would have to spend if you were not Google is as high as $26 million. With Bloom, we know, and GPT-3, it's probably between $1 and $5 million, depending on the arrangement that you have. Bloom is open source because a consortia of over 1,000 different scientific institutions got together and created it. So now everyone is on an equal playing field with these models because of open source. And same with Stability AI, which is the image generator that's behind Mesopotamia. We all have that because of open sourcing. It takes way too much money for a small company to build a new model like this. So mostly people use pre-trained models. So that means taking something like one of these open models and fine-tuning them, which is a very small version of training, or prompt engineering them like we did yesterday. This is also a form of training that's very impermanent. Fine tuning is permanent and it gets you a little bit deeper. The way I think about fine tuning is neural networks come in layers, right? So when you build your neural network like a GPT-3, it's going to have hundreds of layers. Let's say it has 500 layers. If you want to retrain it, you have to do every single one of those layers. With fine tuning, you kind of scrape off the top two and then you put your own data on there, which makes it better at something you want it to do and a little bit worse at everything else. So if you want it to talk more like a certain author, or if you want to have a particular company voice, if you have a defined company voice tone, then you would make sure to fine tune it on that language. And then the last one, which is where we will focus our attention, is on user interface and user experience. No one really knows how this will look. It's a very open field and with lots of room for experimentation. And most today are in a very experimental format. So there's still a lot of value. There's years of value that you could take advantage of just at the user interface level, not adjusting the models in any way. And with Mesopotamia, that's the kind of thing that we're looking for, is things like that template where we can't afford to retrain the model, but we can find ways to help people interact with it better.